Welcome to Cheenta Statistics and Data Science. Today we are going to solve this problem from ISI Mstat 2019, problem 1. The problem says that let A equals to Aij be an M cross N matrix with all non-zero entries. Let B be obtained from A by replacing A11 by 0 and keeping all other entries unchanged. If R is the rank of A, then what is the set of possible values for the rank of B? So basically it means that A is this given matrix, is A11, A12 up to AMN, and B is just the same matrix, but replacing A11 by 0, this part. The remaining terms are all the same, right? Now let us define that let A0j denote the jth column of matrix A. That means A can be written as A01, A02 up to A0n, right? This A01, these are column vectors. I'm just writing this matrix as a vector, where each individual element is also a vector, right? This is a vector, this is a vector, this is a vector. Now, similarly, B also can be written as B01, B02 up to B0n, right? This is B01, this is B02, and this is B0n. Now, obviously, it's clearly easy to see that B0j is equals to A0j for j 2, 3 up to n. That means this A02 is same as B02, A03 is same as B03, and so on. A0n is same as B0. Why? Because B differs from A just by this part, right? This obviously this A01 and B01 are the only different vectors here. Otherwise, they're same. So B01 is not equals to A01. Now, given the rank of A is equals to R, that means what? It means that the dimension of the column space of A is actually R. That means dimension of span of this set, this A0, this set of columns of A, this A01, A02 up to A0n is R, right? It is R. Now, it just means that S, let us suppose that this set is S. So rank of B similarly is dimension of the span of B01, A02 up to A0n, right? Because obviously the B02, B03 are all the same correspondingly. So I'm just replacing those by A02, A03, and A0n. So the rank of B is the dimension of this span of this set. Now let us define that T to be this set A02, A03. That means just taking out the A01 vector from the set S, and the remaining set is called T. Now case 1, let us take first case that A01 belongs to the span of T, right? So this set, the span of this entire set creates subspace. Similarly, the span of T also creates a subspace, right? Now, if A01 belongs to this span, that means if this A01 belongs to this set, that means A01 can be created as a linear combination of these vectors, right? That means A01, this vector does not bring anything new. It can be created by a linear combination of these vectors. So the subspace created by this set and the subspace created by this set is basically the same, and hence the dimension is still R. That is right. The dimension of the span of T is also R because A01 belongs to the span of T. Can be created, so it brings nothing new to the table. It just can be the same. It's just the same. So the dimension is still R. Now B01 is obviously not equals to A01. Therefore, we don't know if B01 belongs to the span of T or not, right? We don't know that. A01 belongs to the span of T, but we don't know about B01. So if B01 belongs to the span of T, then obviously again it brings nothing new to the table, and hence this set B01 and this set, the union of T and this particular vector, is still the same subspace, and it just the dimension is again is going to be R, right? Because it brings nothing new to the table. It can be created by these vectors again, right? So it contributes nothing new. Now if B01 doesn't belong to the span of T, then this union is something interesting. In that case, the dimension actually increases because this set cannot be, this vector cannot be created by this set. So the dimension, this subspace is not the same anymore. It is something new, and the dimension actually increases, right? It's R plus 1. That means the rank of B is either R or R plus 1. So this is the first case, this case 1. Case 2, if A01 does not belong to the span of T, then it must be the span of dimension of the span of T is R minus 1, right? Because ultimately the dimension of S is dimension of the span of S is R, right? This entire thing, the subspace created by this entire set is R. The dimension of this entire subspace created by this set is R. Now, if A01 doesn't belong to the span of T, that means it must have dimension R minus 1, right? Otherwise, if it has R, then it doesn't make sense because A01 contributes something, it has its own importance. So it has to be R minus 1. Again, just a similar case, B01 either belongs to span of T or it doesn't. If it belongs to the span of T, then it brings nothing new. And so the dimension is the same as before, R minus 1, because initially it's R minus 1, so it's just the same. And if it doesn't belong to the span of T, then it brings something new, and hence it increases by 1, so it becomes R. That means again, rank of B is R or R minus 1. Therefore, ultimately, taking all the cases, both the cases, we have that R, the dimension, the rank of B is either R minus 1 or R plus 1, right? It brings us to this conclusion that the rank of B is either R minus 1 or R plus 1, right? So there you have it. The answer is this second option. So there you have it, the solution of this problem.